To be able to effectively use valence bond theory, we need to understand the hybrid orbitals. So let's start our discussion of the hybrid orbitals by reviewing the three hybridization states that we're going to need to consider as we go through the course. So I'm going to draw another Lewis structure of methane. So this is just like the one we did in the very first part of the course. So here's methane. And so you might remember that the carbon in methane is sp3 hybridized. As such, the geometry around it, the arrangement of the groups around it, is tetrahedral. And the bond angles, for example, HCH, are all going to be in the neighborhood of 109.5. So let's make a summary, actually, of the three hybridization states and their geometries and bond angles. So these are the three hybridization states we'll use in the course. So an sp hybridized atom has a linear geometry surrounding it, and the bond angles around it are 180 degrees. If an atom is sp2 hybridized, it has a trigonal planar arrangement of the groups around it, with bond angles that are going to be approximately 120. And then sp3, we just talked about up above, that has a tetrahedral geometry and bond angles of 109.5. Okay, so these are the three hybridization states, their geometries, and the bond angles associated with them that you need to know for the course. Okay, so now let's go back to valence bond theory. So Linus Pauling was one of the ones that came up with hybrid orbitals. And Linus Pauling actually had his hands in a lot of different projects back in the day, one of which, as we can see from the picture shown to the right, was elucidating or helping to elucidate the structure of DNA. So hybrid orbitals is just one of the things that he was involved in. So Pauling recognized that if the carbon atom in methane were unhybridized, the picture of bonding would not look the same as what we know it to be. So let's take a look at this. First of all, let's look at the set of orbitals shown up above. So let's say that these are the orbitals in carbon's valence shell. So we have a 2s and three 2p orbitals, px, py, and pz. Now, notice that because each of these p orbitals is directed along one of the axes of the coordinate system, all the p orbitals in the unhybridized atom are mutually perpendicular. Now, it's not just carbon, it's any unhybridized atom that has p orbitals. The p orbitals will all be perpendicular to one another. So now let's think about valence bond theory and think about the structure of methane. Valence bond theory tells us that bonds are formed by overlapping orbitals on adjacent atoms, the atoms participating in the bond. That means that an orbital on carbon is overlapping with an orbital on hydrogen to make each of these bonds. Now the hydrogen is always going to use the same orbital. It has one electron, and that one electron is always in a 1s orbital. So let's say that we have hydrogen with a 1s orbital. And let's say that our unhybridized carbon atom, for a couple of these bonds, is using its p orbitals. So here's a p orbital on a carbon. And let's say that it's using a different p orbital to form another bond with another hydrogen. So this is also a p. Notice that they're perpendicular to one another. And here's another hydrogen with a 1s orbital. Okay, so the area of overlap is where I'm highlighting. So that would be the case for two of the bonds in methane if the carbon atom were not hybridized. But what Linus Pauling recognized is that that fails to predict correctly the HCH bond angle in methane. It would predict it as being 90 degrees because of the perpendicular arrangement, or the orthogonal, we could say, the orthogonal arrangement of the p orbitals in the unhybridized carbon. So what Pauling concluded here was that a model of bonding for methane that uses an unhybridized carbon would fail to correctly predict the bond angles in methane. So the HCH angles. Pauling further noted that because we know from experiment that all the bond angles are the same, that suggested to him that the carbon is using 4 identical orbitals to form the bonds to the hydrogen. So since all the bond angles are the same, Pauling's conclusion was that the carbon was using 4, or I guess it still is. Methane is still a thing. Carbon is using 4 identical orbitals to form its bonds to the hydrogens. Now, when we think about identical orbitals, we can use a term that we've already seen, and that is degenerate. So 4 identical orbitals, 4 orbitals that are equal in energy and in all other respects are all the same. So what we're going to do is look at how Pauling constructed these ideas of hybrid orbitals. It turns out it's a mathematical process, but we're going to hand wave past the math. We don't have to worry about the math. All we really care about are a couple of things. First of all, that the math exists, because that's going to help us to understand when we do the same sort of process when we get to the molecular orbitals. So we want to at least recognize theoretically that this is what's going on, that this is how we're rationalizing the creation of these new orbitals. But the other thing is, just so that we know, what are the orbitals that are present on atoms of various hybridization states? So that's why we want to go through and build these models up. So we're going to start by looking at a valence bond model of the bonding in methane. So here's the molecule. And once again, because early on we could never repeat these things too much, this is an sp3 carbon atom. And so it has a tetrahedral geometry and bond angles of 109.5 degrees. Okay, now hopefully you all passed the art prerequisite for the class because you're going to be doing a lot of drawing. And you're going to be doing a lot of drawing in 3 dimensions. So here's a first glimpse at how we're going to depict a molecule in 3 dimensions. And it's going to look like this. So to show the bonding, to show the groups around a tetrahedral carbon, or an sp3 carbon, we draw it in the way shown to the right. So the 2 bonds that I've highlighted in yellow are in the plane of the paper or the screen. So these are in the plane of the paper. This bold bond is called a wedge. That's coming out of the plane and toward us. So a wedge bond is coming toward you. We'll say coming toward the viewer. And then this bond back here is called a dash. The dashed bond is going away from the viewer. So you have, for around a tetrahedral carbon atom, or any tetrahedral atom, or tetrahedral atom with tetrahedral geometry, I should say, 2 bonds will be drawn in the plane, 1 forward, 1 back, just like this. Now, the one that's coming forward is typically right in front of the one that's going back, but we can't draw that. Otherwise, we wouldn't be able to see in our picture the bond that's going back. So you draw them offset from each other, And I just drew a couple of little lines. That's the place of the offset so that you don't have just this and you're trying to see the dashed line behind it. So we typically offset it so that that's not a problem. Okay, so that's your first tetrahedron, and you're going to be drawing many, many more, and so we'll get to that a little bit later. But for now, let's talk about the bonding some more. Okay, so the first question you're going to ask is how many areas of electron density are there around the central atom, in this case the carbon? So first of all, let's define our terms. What do we mean by an area of electron density? An area of electron density could be a bonding region. Now, a bonding region could be a single bond, a double bond, or a triple bond. Each of these counts as only one area. So each type of bond counts as just one area of electron density. So what do I mean by that? I mean that a single bond is one area of electron density. A triple bond is one area of electron density, and so on. So you don't get 3 areas of electron density just because it's a triple bond. Another area of electron density could be represented by a lone pair of electrons. And then finally, a radical or an unpaired electron is a third type of area of electron density. So in methane, we count how many areas of electron density we have around the carbon. And we see we have 4 bonds coming from the carbon. So we can say that in methane, the carbon has 4 areas of electron density. And so what this tells us is that it needs 4 degenerate hybrid orbitals. So the number of areas of electron density tell us how many hybrid orbitals we need to construct. All right, so how are we going to construct them? We're going to construct the orbitals using a mathematical process. And the process involves taking what's called the basis set. So we're going to use what's called the basis set of carbon's valence orbitals. Now, let's think about what those orbitals are. So over here on the left, I'm going to reproduce our picture of an unhybridized carbon. So we did this in the last video. We did an electron occupancy diagram for carbon and put electrons into a ground state carbon atom. Okay, so there they are, all the electrons. And so the valence shell in carbon, remember, is the one that has the outermost electrons. So that's going to be all the orbitals that have the highest principal quantum number in the carbon, which would be the ones with the principal quantum number of 2. So there are the 4 valence electrons in carbon. And so the valence shell, or the valence orbitals, for an unhybridized carbon are the 2s and the 2p orbitals. Okay, so we have 4 of them. There are 4 orbitals available to us in the valence shell of carbon, even though we're not presently using all of them. So we have an s orbital, and we have 3 p orbitals. So that's always going to be the basis set of valence orbitals in a carbon atom. What we're going to do with those is subject them to a mathematical process that's called mixing, or we could call it combining. And so we're going to do some mathematical operations to convert these orbitals, and remember these are functions. And so what we're doing is mixing or combining functions to get new functions. So we're going to do that in order to get our hybrid orbitals. Okay, so which of the orbitals in the valence set, the basis set, do we use and which ones do we not? Well, that depends on how many hybrid orbitals we're trying to make. In this case, we need 4. So we're going to use the s. We're always going to start by pulling the lowest available energy orbital out of the basis set. So we're going to need the s, we're going to need the p, another p, and the third p. So because we need 4 orbitals as our result, we need to use 4 orbitals from the basis set. So let's make a note of that. We need 4 hybrid orbitals. So we use all 4 basis set orbitals. So we're going to mix these together in various algebraic ways, and what we end up with are our 4 hybrid orbitals, which have the label sp3. So now that the carbon atom is hybridized, these are now the 4 valence orbitals on an sp3 carbon atom. So the 4 valence orbitals on an sp3 hybrid atom. Okay, so an sp3 orbital, let's think about what that means. So we used 1 s and 3 p orbitals and combined those, put them all in a blender, and it spit out these 4 results. So the results are 1 part s and 3 parts p. Those are our ingredients. Or we could put this in a different way. We could say that an sp3 orbital has 25% s character and 75% p character. So what does an sp3 orbital look like? Let's draw a picture of that over here. So starting with an s and a p, when we mix those together, what we're going to end up with are 4 orbitals that look something like this. Okay, now I'm going to go ahead and shade one of the phases, one of the lobes of the p orbital, because we're going to have a similar result in our new sp3 orbital. Okay, so this is an sp3, and it has 2 lobes, just like a p orbital does. The larger lobe is the one that's used for bonding. So this is the lobe of the orbital that's going to overlap with an orbital on another atom to form a bond. The nucleus is right between the lobes. And also remember that with the p orbital, there was a plane that separated those 2 lobes. The same thing is true in an sp3 orbital. There's a nodal plane that separates the 2 lobes of the orbital. So notice that when you cross a nodal plane, you're going from one phase of an orbital to a different phase. Okay, now let's draw a picture of the bonding in methane according to valence bond theory. So this is going to be fairly crude, but we'll do the best we can. So the carbon now has 4 sp3 orbitals, and they're arranged in a tetrahedral fashion. So here's a picture of methane. And so I'm going to try to draw our picture of the bonding in the same way. So here's a pair of sp3 orbitals. These are in the plane of the paper. And then we're going to have one coming out. So I'm going to draw the outline of it in bold. And then there's one going back, and I'll just draw that with a dashed outline. Each of the sp3 orbitals contains one electron. Now, what you might be noticing is that I didn't draw the back lobe of the orbital. That would clutter up the diagram, so oftentimes people don't include those little back lobes. The back lobe, by the way, is the one that's not the larger lobe. So over here, sometimes people refer to this as the back lobe. Okay, so it's not really doing much. So we're going to leave it out of the diagram just to help the diagram look a little more uncluttered. Okay, so there are 4 sp3 orbitals. So sp3, 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 and sp3. Those are overlapping with 1s orbitals on hydrogen atoms. So here's a 1s on a hydrogen with 1 electron in it. And here's another one over here. And then a third. And finally a fourth. Okay, so this is a fairly crude picture of the valence bond model for the bonding in methane. And so what we would say is the following. According to valence bond theory, each of the carbon-hydrogen bonds in methane is formed by the overlap of an sp3 orbital on carbon and an s orbital on hydrogen. So each of the carbon-hydrogen bonds is formed by the overlap of an sp3 orbital on carbon and an S on hydrogen. Now these are single bonds, which means that they only have a sigma component. And so let's include that in our descriptor. So to be absolutely precise, we would say each of the carbon-hydrogen sigma bonds in methane, just added this in, is formed by the overlap of an sp3 orbital on carbon and an s orbital on hydrogen. Okay, now let's continue this discussion by looking at a different molecule. We're now going to look at a molecule called ethylene. Ethylene is the common name. The IUPAC name, or systematic name, is ethene. So ethylene, as it turns out, is the simplest alkene you can have. So it's just 2 carbons and 4 hydrogens, and here's a Lewis structure of this. Now what we can notice in the picture is that there's a symmetry plane in the middle of the molecule. So imagine a plane that's perpendicular to the board or to the page, and notice how the left side of the molecule reflects into the right side, which means that if we just address the bonding on the left side of the molecule, we've already solved what's going on the right side of the molecule. So again, the question is, how many areas of electron density are there around carbon? And it doesn't matter which carbon we're thinking about because they're both in the same situation. Okay, so the answer to that, there's 3 bonding areas. Each of the carbons has a single bond to hydrogen, another single bond to hydrogen, and the double bond to the other carbon. So that's 3 areas of electron density, which means that we need 3 degenerate hybrid orbitals. So again, we start with the basis set. Which for carbon includes s, p, and p orbitals. And then we're going to pull out of the basis set the number of orbitals that we need to make 3 hybrid orbitals. Okay, so if we need to make 3 orbitals, we have to put 3 orbitals into that mathematical process. That's what we did with methane when we were making sp3 orbitals. We needed to make 4, so we had to combine 4 of the orbitals from the basis set, which was essentially the entire basis set. In this case, we only need 3 orbitals, so we're going to start again with the lowest energy one. That would be s, and then we're going to use 2 of the p orbitals. Okay, so the idea here is that the number of orbitals in to your mixing process, the number of orbitals that you put into your mixing process is equal to the number of orbitals that you get out. Okay, so mixing an S, a P, and a P, we end up with 3 sp2 hybrid orbitals, all the same energy. But then what happened to this guy? This p orbital we didn't use. So we just bring that across and put it in the same set with our new sp2 orbitals. And so now these are the 4 valence orbitals on an sp2 hybrid atom. We can describe these in terms of percentage of p, p, and s character. So an sp2 orbital is 33% s character and 67% p character. Okay, now we didn't do this for the sp3 orbitals, but let's do this for the sp2. Let's think about this on an energy diagram. Let's see where that gets us. Okay, so here's energy, increasing from bottom to top. And so when we start out with our valence orbitals, our basis set, remember we have 2s and 2p. Those are the valence orbitals in an unhybridized carbon atom. When we mix orbitals, the sp2 orbitals that we end up with, being 33% s character and 67% p character, are going to be closer in energy to p orbitals than they are to s orbitals. So their energy level will be there. And then the p orbital that we didn't use just comes across. Okay, so this set over here, these are the new valence orbitals on the sp2 carbon. Now when we thought about sp3 orbitals, we drew a picture that looked something like this. So this is sp3. An sp2 orbital has a bit higher percentage of s character. So it's going to be squished down. This larger lobe is going to be a little more compressed than the large lobe on an sp3 orbital. That's because it has more s character, and an s has the form of a sphere. And then if we went all the way to the sp orbital, that has 50% s character and 50% p character, and so that large lobe is going to be the most squished down. So let's throw an electron in each of those orbitals. Remember that the nucleus is between the lobes of each of these hybrid orbitals. So just by looking at the pictures, what we can tell is that electrons that are in orbitals that have more s character have a greater likelihood of being closer to the nucleus. That's going to become important a little bit later. So electrons in orbitals with more s character are held more closely to the nucleus. Okay, now let's draw pictures of the bonding in ethylene according to valence bond theory. Okay, so let's draw a couple of carbon atoms. Now remember, what we decided for one carbon atom is going to be the same for the other carbon atom because of the symmetry inherent in the molecule. So each of these carbon atoms has 3 sp2 orbitals. Now remember that areas of electron density are going to spread themselves apart to the maximum distance they can. So 3 orbitals, the farthest they can get away from each other, is to adopt the trigonal planar arrangement. So we have 3 sp2s on this carbon. Each of those has 1 electron in it. And then the other carbon is in a similar situation. It also has 3 sp2 hybrid orbitals in a trigonal planar arrangement. And each of those also has 1 electron. Okay, now let's bring in our hydrogens. So the hydrogen, again, always uses a 1s orbital because it's the 1s orbital that houses the single valence electron of a hydrogen. Oops. We did not observe the Pauli exclusion principle there, which is a terrible, terrible thing. But I think we're going to be okay. Okay, so H1s. All right. What we've shown is the bonding in this molecule that relates to the electron density along the bond axes. In other words, we've just drawn the sigma bonding in ethylene. But there's a double bond, and so the double bond incorporates not only a sigma component, but a pi component, so that's the next thing we have to draw. Okay, now let's think about the picture we just drew. I'm going to reproduce it here, like so. And we're going to think about what it means to have a trigonal planar arrangement. The word planar means flat. So focus on the carbon that I just highlighted in yellow. If there's a trigonal planar arrangement around it, that means that that carbon, this hydrogen, and this carbon all occupy the same plane. So you have a plane here. And then as to the other carbon, that carbon, this hydrogen, and this carbon are all in the same plane. So there's another plane. Notice that those planes overlap, meaning that really you just have one plane. So the molecule is planar, it's flat. So to understand the pi bonding, what we're going to do is draw this a little bit differently. We're going to tip this molecule, which right now is drawn flat in the page, we're going to tip it so that it's perpendicular and draw that over here. And so what that means is that 2 of the hydrogens are going to be going back and the other 2 are going to be coming forward. each of the carbon atoms has the leftover p orbital, the one that we did not use when we did the hybridization process. So they both have that. And each of those p orbitals contains one valence electron. So I'm just spreading them out like so. So the area of overlap, I'll draw this in a different color, would be here and here. So this is the pi bond. So the p orbitals are perpendicular to the plane shown over here. The molecule is flat. And for the p orbitals, those quote-unquote leftover p orbitals on each of the carbons, for them to get as far away as possible from the 3 sp2 orbitals around each of the carbons, they're going to have to be at a 90-degree angle to the plane formed by those 3 sp2 orbitals. So the molecule is planar, and the p orbitals are perpendicular to that plane. So the picture we drew to the right shows 2 of the hydrogens coming forward, 2 going back, and then the p orbitals that we drew are in the plane of the paper. So this is the pi bonding in ethylene. Okay, so according to valence bond theory, how would we describe all of this bonding? First of all, we're going to have to segregate things by sigma bonds and pi bonds. So we have a carbon-carbon sigma bond, and that's formed by the overlap of an sp2 orbital on one of the carbons with an sp2 orbital on the other carbon. We have 4 carbon-hydrogen sigma bonds. Each of those is formed by an s orbital on a hydrogen and an sp2 orbital on carbon. And finally, there's a cc pi bond. That's formed by a p orbital on one of the carbons overlapping in a side-to-side fashion with a p orbital on the other carbon. So this would be our valence bond theory explanation or description of the bonding in ethylene. So let's take a little bit of a break there, and then in the next video we'll finish up our discussion of the hybrid orbitals, revisit an idea about resonance, and then we'll be ready to move on.